Okay, welcome everyone to the AI seminar. AI seminar, we try to analyze and be aware of the big forces shaping the field of AI. Some of you may remember the predictive representations hypothesis from quite a few years ago, and I'm sure you remember the bitter lesson. These are all trying to think deeply about what's going on and what are the implications. So I think of all those things, and I think of what Khurram's going to talk about today, another big hypothesis that we can explain what's going on, what we should focus on in the future. So Khurram, as you all know, we all know Khurram. He's a PhD student here, and he's worked with Martha for his master's thesis, and now he's working with me for his PhD. Anyway, I'd like to all give Khurram a big warm welcome.
Thank you, Rich. So today I'm going to talk about some of the ideas that have been motivating my research. So it's going to be less about my research and more about why I'm doing what I'm doing. And some of these ideas have been developed by discussing them with Rich, Martha, Zahir, Rajwan, Shivansh, and a lot of other people. But this is my take on this perspective of doing research on artificial intelligence. So let's start. I have four. This is not working. Yeah, I have four parts of the talk. The first part is just to tell you what the big word hypothesis is and why is it important.
How do you change the volume?
Sorry?
Oh, Jesus Christ.
Okay, I think they were not talking. So yeah, the second part is why you should care about the big word hypothesis if you assume it to be true. The third is what are the consequences of this hypothesis on reinforcement learning research? And then finally, how should you benchmark algorithms if your goal is to develop algorithms for the big words? So let's start with the hypothesis. The hypothesis is very simple. It's the idea that even though our agents are complex and large, they are still orders of magnitude smaller than the word or the environment that they operate in. So what that means more concretely is that even in the limit of data, the agents are not capable of modeling the word perfectly. They're also not capable of sensing the state of the word perfectly. So if you try to learn a model from state of the environment to the next state, and you used all the data that you can ever get, your agent will still not be able to get that correctly. Similarly, if you try to keep your complete history, you would still not be able to sense the state of the word perfectly because there is too much going on for a small agent. And finally, it means that if you try to learn, well, you're not going to learn to achieve your goal perfectly. You would have to approximate, you have to use approximate solutions and come up with some suboptimal solutions. Now, this big word hypothesis can be trivially true or false because you can just pick a problem in which this is true. So for example, 100 by 100 Go board. That's a very large problem. So probably those three statements hold true in that case. You can also pick a problem in which it's not true. So for example, you can take a thermostat and it's a very simple problem, small state, small action space, and you can probably learn, do a lot of things. And then we also have tabular RL algorithms and benchmarks. So clearly there are problems in which it's not true. So really what this statement is, it's more a statement of what kind of problems should we care about? What are relevant problems in artificial intelligence? Or what do real world problems look like? Do they look more like the kind of benchmarks that we're used to, where the agent is very large and it's over-parameterized? Or are they more similar to this big word hypothesis, where the agent is small and the environment is very large? And even if you think that, well, it's not clear to you that this is a property of a problem we care about, you can still think of it as an ambition. That, okay, my goal is to come up with solution methods or algorithms that can operate even when this difference in size exists between the agents and the word. And because we can use these algorithms for all sorts of problems, so then you can just think of it, big word hypothesis, as things that this is the subset of problems I'm interested in. Now, very similar things have been said in the past. So for example, Rich gave a talk 3 years ago, which was called, "Are you ready to embrace function fully embrace approximation?" So these are not new ideas, but they're still not accepted in the community completely. So is there any evidence of of the idea that problems that we should care about are similar to big word hypothesis in existing literature. And also, is it possible that this hypothesis that I'm proposing, it's really a temporary thing because our computers are not good enough yet? And then maybe in 20, 30 years, this would not be a problem because computation would have grown exponentially. It has been growing over the last 40 years. And then maybe we can model these large problems exactly and solve these large problems exactly. But I'm going to argue that that's not going to happen. And a simple reason why that's not going to happen is that even though historically computation has been growing exponentially, our ability to sense the world has also been growing with computation. So for example, you can design sensors that can sense the world at a specific resolution or a specific frequency. And as you get more computation, it becomes possible to increase both of those. So to give you an example, if you take a modern smartphone, they can record a video at 4K 60 FPS. Now, this is not because the sensors for recording videos at 4K 60 FPS didn't exist before. We've had these sensors for decades, and we've had these sensors in phones for over 10 years ago. But the reason why this was not possible before is because we simply did not have computation to be able to process this information, compress it, store it. And we already also have sensors that can do much more than 4K. They can get data at 8K resolution, for example. But the reason we don't do that right now is because we don't have enough computation. So you can imagine that as our computation grows, so would our ability to sense. We would have sensors which are high fidelity. And so the problem would keep getting harder and harder because you can sense the world more. Now, I also want to emphasize here this point that we think that maybe big word views is not important because we can just have large models. And one example people point out to is language model. But language models also don't really operate in the big world. So if you look at the data set that was used by GPT-3, which was one of the largest models for which we have publicly available information, the same amount of data can be generated by your phone in about 1 week. So this data set that it uses is really not large. When I say big words, I mean significantly bigger than even these data sets that people use for language models. And another observation is that right now we are very far from sensing the world at its full scale. So we have these cameras, but they can only sense one part of the world. And you can imagine that until we hit a point where we can sense the world at its full scale, increasing computation is not going to solve our problem because we're just going to be able to sense the world more. And so we can use the computation to do that instead of hitting the word perfectly. And then another subtle point is that, and this might not be obvious at first, that the word itself becomes more complex with more computation. So let me give you an example of an agent, let's say, that's trying to play Go against a fixed opponent. Now, if the opponent is fixed, then the opponent is part of the environment. And let's say the opponent is using some simple heuristics to play the game. Now, if that's the opponent you're playing against, modeling that environment is not that difficult. So you can play with that opponent, gather data, and recover those heuristics. And then you can make perfect prediction about how the environment would change based on your actions. Now, if I change that opponent to, let's say, alpha 0, now the environment becomes significantly more complex. Now, the only way you can model the environment perfectly is if you can model the alpha 0 agent, which itself is very complicated. And then you can imagine that as computation grows, your environment can become similarly more complex because it will have agents that are equally complex or more complex because of more computation. So this is just two small arguments for why I think that just growing computation is not going to solve this problem. And we have to just accept that this problem is going to be there and develop algorithms that can operate in this big world. Now, is there any behavior from existing algorithms or existing research that supports this idea that this hypothesis is true, that some problems we care about are really large? There are two big ones, and this is more speculation than direct evidence because I didn't test my hypothesis about these algorithms. But my claim is that if the big word hypothesis was true, if the problems that I'm going to show right now were bigger than the agents, then the behavior that we're going to see is the behavior you would expect. So one is the scaling behavior that we are seeing in these large language models, where you see that. Okay, so this is a plot from one of the GPT-3 paper where on your x-axis, you have the amount of computation used by your model, and on the y-axis, you have the validation loss. And each of these lines correspond to different models. And the more yellow the line is, the bigger the model is. And what you see here is that as you increase your model size, your performance improves. And if your model is very small, then even if you do a lot of computation, it stops improving after a certain point. And if it was the case that your model didn't have enough capacity, then that's the kind of thing you would expect, that it would improve to the point where it can fit the data, and then it would stop improving because it doesn't have the capacity. So it seems like even these large language models are already hitting the capacity issues. But here the problem could be something else. Maybe the issue is that they have the capacity, but they just don't know how to use it properly. So the second example that I'm going to share, I think, is even more clear. So this example is the performance of AlphaGo 0 versus this raw network that was trained to match the target of AlphaGo 0. So let me share a plot from this paper. So there are two systems here. One is this raw network, which is basically a neural network which outputs what move to make for a given position. And one is this AlphaGo 0, which is this raw network combined with the scene time planning. So before making a move, it uses a model to do a search, and then it picks a decision that's better than what this raw network predicts. And the way this raw network is trained is they use the AlphaGo 0 to output the best action, and they update the raw network to match the prediction of AlphaGo 0. So the raw network is literally being trained to fit what AlphaGo 0 does. And you would imagine that if the raw network has enough capacity, then over time, it would be able to catch all the knowledge that AlphaGo 0 has, and the performance would match. But what you see empirically is that even when they train these networks for a long time, the performance plateaus, and this difference does not go away, which is again something you would expect to observe if the problem of Go was much larger than the network that people were using to fit the problem of Go. Okay, so this is the introduction of the big bird hypothesis. Now, yes.
The raw network doesn't do any MCTS, and that's why it cannot match the performance of AlphaGo 0.
Yes, but the raw network is being trained to fit the output of AlphaGo 0.
Without any online play, without any MCTS search.
The targets are generated with MCTS. So
But raw network itself doesn't do MCTS.
Yes.
Okay.
Right. But
This is an interesting result. Do we know anything about how this scales when the raw network is increased in size or something?
we don't, because we can't run those experiments. But if the reason was due to capacity, then we would expect that once. Actually, no, we do have some indirect evidence that they applied a very similar algorithm mu0 on, again, Go and Atari. And in Go, they observed the same thing for mu0, that the raw network is worse than AlphaGo 0. In Atari, the raw network performed about the same as the mu0 plus MCTS search. So in Atari, they observed that this difference between the performance goes away, and you don't get a lot of benefit of the same time planning. And which, again, would be consistent with the idea that, okay, Atari is not very big, Go is very big. So in one case, you're hitting capacity limit, in the other, you're not.
Right. So, but maybe in case of Go, if there was a larger network, maybe that could happen.
That's what we would expect. That's, I think, if I'm speculating correctly, then we should see that a larger network should reduce this gap. And if it doesn't, then maybe there is something else happening.
Hopefully, it's equal test by the 5x5 Go.
But the thing is that, yes, if you reduce the network, I guess if you took the same network, you did 5x5 Go, and you didn't see this difference, so it was not as large, that would show the same thing. Yes. Okay.
So would that be, so what would that tell us? Let's say that was the result we saw. Then if someone concludes, okay, so I just need to make my network larger, would that be a reasonable conclusion?
Sorry?
If we saw the result that Shivam said that, oh, 5x5 Go, big enough network, we can match the performance of Alpha 0. If someone concludes, okay, we just need to make our networks bigger, is that a reasonable conclusion?
Well, but that's the problem, right? The word is so much larger that the idea is that you can make your network bigger, but the word is still going to stay complex.
Right. I mean, so that's I guess that's what makes the argument hard, at least in the discussions I've had, that you just can't get the point across to people that they can't just make their networks larger and make the problem go away. But let's say this was a paper that came out, then it could just increase their belief in that thing, right? So how do you talk to these someone like that?
I mean, I think that's fine. Like, people are always gonna, there are people and they have some reasonable arguments that, maybe the word has a simple underlying structure. The observations are complex, but the word is not. And if I can learn that, then I don't need something big. So all those positions are reasonable and people are exploring them. But I think that it's a bit of a wishful thinking to just hope that there's a simple structure in the word. It's a bit of a wishful thinking. And without that assumption, this should be the default position. Yes.
Just not on the substance you're talking, but I think you can get rid of that thing that's obscuring the top of your slides. You go under the more, there's something that'll let you hide it. Hide those floating eating controls. No. Yeah, try that one.
Yes, that worked.
Good.
Thank you. Okay, so now I'm going to the next part, which is, well, why should you care about this hypothesis? Maybe it's true, but then for you as a researcher, it's not really that important and you can just work on your algorithm. And I'm going to talk about two implications of big word hypothesis. One is that, well, if it is true, then approximate but computationally efficient algorithms have an advantage over algorithms that might be better in terms of they're making fewer approximations, but they're computationally more expensive. And then second, that online continual learning emerges as a promising solution method. So if you assume that the word is big, then you don't have to say, I'm doing continual learning because that's my problem. You can show that it's exactly the right thing to do if you want to maximize your performance. So let's look at the first one first, that approximate solution method have an advantage. And the general idea is that, well, if you reduce the complexity of your learning algorithm, then you can repurpose the amount of computation you save to make your agent larger. And because we're assuming that the agent is constrained by capacity, by increasing the size of the agent, you can hope, maybe it's possible that you can show that, well, now this bigger agent with this worse algorithm performs better than the smaller agent with a better algorithm. And so an example of that could look like you could reduce your batch size to increase the number of parameters, or you can reduce the truncation window in your backprop through time to increase the number of parameters. Now, can we show that empirically? The answer is yes. So let's look at that. So I'm going to compare two algorithms for recurrent learning on Atari here. And just to give you a background, you have a recurrent network, it's getting some observations, and then it has some hidden data, it's making some predictions. And then if you write your gradient of your prediction with respect to your parameters, it looks something like this. And then there are two ways you can compute this gradient. One is backpropagation through time, one is RTRL, and the difference between them really is the direction in which you do these multiplications. And backpropagation through, and they make different trade-offs in terms of time and then memory and complexity. They're both not tractable, so what people do is they approximate them. So they approximate backpropagation through time by using computation. So they just assume that gradients before certain points are zero, and then and this assumption is in fact true for many current architectures because of vanishing gradients. So gradients do vanish after a certain number of steps, so 20 steps, let's say. So if you're truncating after that steps, your gradient estimation is quite good. And the other method is a linear approximation to RTRL. So if you imagine this is your recurrent network, this is your prediction, these are the two hidden units, and this is your input, then what linear approximation to RTL says is it assumes that any parameter that is not connected to a hidden state directly. So for example, this theta 2 is connected to H3, but not H1, but it can still influence H1 through H3. Linear approximation to RTL is going to assume that those influences that do not exist. So a parameter can only influence a hidden state if it's directly connected to it. And it's a very crude approximation. So for example, in this case, it's just going to assume these 6 gradients are 0, but in fact, these are not 0. And if you look at existing literature, what you would find is that truncated backdrop through time performs much better than this linear approximation to RTRL. And the difference is quite large. But the problem is that, number one, those experiments are done not under these big word conditions. So the network is often over-parameterized. And second, when they use a cheaper algorithm, they don't use the computation they save to increase the size of the network. They just compare two networks with about the same architecture and train them with two different algorithms. And so the comparisons are not really fair. So my claim is that if you were studying them under the big word conditions, then maybe the ordering would change. So maybe our conclusion that truncated backdrop root time is better than this approximate algorithm is not correct when you go to the big word conditions. So let's look at that. So I'm going to do an experiment. I'm not going to explain the benchmark in detail now. I'm going to do that towards the end of the talk, but basically it's an Atari benchmark. I'm doing policy evaluation, and I'm using a policy which is taken from a pre-trained Atari agent. So a rainbow Deacon agent, and then use that to interact with the word, and then use GLambda to learn a value function. And then I'm going to learn a value function for 50 million steps and measure and report the mean squared return error for the last 1 million steps. So average return error over the last million steps. And then I'm going to constrain the amount of computation that's allowed to make sure that the agent is smaller than the word. So now, so RTRL is the real-time recurrent learning. Yeah. It's
you're taking the whole history and you compute the value.
So RTRL is, if you use the full RTRL, yes, it computes the actual gradient as if you were using the whole history, but it does it online. But it's a very expensive algorithm. So I'm reporting results for a very crude approximation of RTRL. Right. And in fact, this algorithm, this linear approximation to RTRL, is a very old algorithm. This is the algorithm that was used in the original STM paper in 1997. Backdrop root time became more popular later on. Okay, so this is the experiment setup, and then on the x-axis you see all the Atari games. And what I'm going to do now is, I'm going to normalize the errors with respect to the error achieved by truncated backdrop. And all these results were all the important hyperparameters for both methods were tuned, and they're averaged over 30 feet. So these results are the best that each of them can do when you tune the parameters. So what this means is that if the error achieved by truncated backdrop is 0.2, I'm just going to normalize it to 1, and then normalize the other error with the same factor. Now, if you look at the results, they look something like this. So linear RTRL, which everyone believes to be the worst algorithm, performs much better than truncated backdrop root time in almost all of the games. And if you look at this side of the game, it performs significantly better than truncated backdrop root time on those problems. So to summarize, one implication of caring about this hypothesis is that your ordering of algorithms can change when you benchmark them under the conditions that satisfy these hypotheses, and when you benchmark them in the over-parameterized setting.
Could you repeat the constraint that you have per step, like for computation?
So right now in this experiment, it's 50,000 operations per step.
Okay, so that includes, like, multiplications, additions, like all everything. Okay.
And then again, so you might ask, why is it doing better? Well, we already talked about it, that if you're using cheaper algorithm, the function approximator can be larger. In this case, linear RTRL has more parameters, which is probably why it's outperforming the other methods. And again, this only holds if the conditions of big word hypothesis are satisfied.
These are neural networks?
Yes, these are recurrent neural networks. So both of them use LSTM. Okay, and the second implication of this idea is that continual learning emerges as a promising solution method, not just a problem setting. And we can show that in a very toy example, but let me just explain the concept first. So imagine that this grid word represents your complete state space. And you can move around in this state space by moving left, right, up, or down, but you can't teleport and jump around. And also imagine that your agent is small, so it cannot represent, and every state has a corresponding target. And because the agent is small, it cannot represent the optimal solution. So it's going to have some error that it cannot reduce because of capacity issues. So then you can imagine that if you sample data IID from the state space and you learn to convergence, your error might look something like this, where white means high error, low error, and then you might have some error on all the states. It's not going to be 0, but it's going to be maybe uniformly distributed because you're training like that. Now, if you were learning online, you could do something different. You could have used your capacity to do better on the part of the environment that you're in right now at the expense of the parts of the environment that you're not in right now. And this is the general idea of range tracking, as was shown in this paper that's mentioned below very nicely. And then once the agent goes to the other end, then if it's learning online, it can adapt its solution over time. And then maybe you can show that under these conditions, this online tracking agent can be better than the fixed solution. So let's actually do this experiment, the one I just described. Let's say our grid word is 500 by 500. We have a state ij, and then we're going to generate targets using randomly initialized neural network, which has about 40 neurons. So I'm going to take all the states, pass them through this fixed network. It's going to give me a real number. That is the output for that state. And that output is fixed. So this is a supervised learning. And the policy is just random walk. And now and then we're gonna evaluate the average online error. So the error they accumulate over time. And I'm going to compare two algorithms. One is fixed solution, and the fixed solution kind of cheats because I'm going to give it the complete data set before I start evaluating it, and then it's going to converge to the best set of ways that it can converge. So it has already a head start. It already knows the data before interacting with the word. Now on the x-axis, you see the size of your agent in terms of number of hidden units, and the y-axis is the error. And you see that when your agent is very small, the error is high, and the agent is very big, the error is very low. That makes sense. Now let's compare this to an agent which is simply doing online STD. It's interacting with the word, makes a prediction, and it updates based on the target of that prediction. Well, that one looks something like this. And when the agent is small, it does better than the fixed solution. When the agent is very large, then it does worse than the fixed solution. Now, my basically argument is that most of our benchmarks and methods, they fall somewhere here, which is why we see that these online tracking algorithms are not useful and offline learning works very well. Whereas problem consistent with the big word view, they fall on the other side of this spectrum, and online tracking can be far superior to finding a fixed solutions. Okay.
That's a big other, right? Like, environment changes much more slowly, or the target changes much more slowly compared to how fast it's done.
So yeah, the environment is not changing here. The targets are fixed, but yes, the agent is moving in the environment, and the assumption is that it's moving. There is some temporal coherence. So if the agent could at every point could teleport to a random point, then clearly you will not see a benefit of tracking. So the targets are fixed, the environment is fixed, but the policy is random walk. Because the policy is random walk, then you can expect that it's going to stay here and then it's going to go somewhere else, but it's not going to go directly from here to here. There is some temporal coherence in your data stream, which allows it to fit to the part of the word that is currently in. And because the targets are generated using a random neural network, they're also probably smooth. So the targets for the states that are in this area are probably close to each other in this area. But I didn't optimize this experiment at all. I just set it up, ran it once, and then these are the results I got, and I just used them. Okay, perfect. Now I'm going to go to the third part. This is very short. This is really about what I think are the immediate things we need to do if we want to improve our algorithms for reinforcement learning in big words. There are three things that I think are important. One is that we need to develop algorithms that are computationally efficient and that can track, so that can do online learning for this part of our reinforcement learning. We want perception. So the agent is getting a stream of data, action and observation. It has to build the agent state. It has to build a state of the environment. And we want to do that computationally efficiently because we want that state to be as large as possible. So we could use a more expensive algorithm, but again, then the state would be very small and we don't want that. And this is the part that mostly what I've been working on over the last 1 to 2 years. And how do we develop algorithms for perception that are better? And the recurrent learning experiment, you could also see that as comparing two algorithms for perception by doing policy evaluation. The second thing is this transition model, the model-based RL. Now here, if you look at a lot of the research in model-based RL, what people do is they take an agent and model-free agent, they add a model on top of it. So now they're doing extra computation, and then they show that this computation is helping them. But this again has the same problem that now that you're doing more computation, then your model-free algorithm should probably get some more resources. So we have to develop algorithms that when you learn a model and you make predictions, you do planning with that model, then the computation that you're taking away from the agent by doing this extra computation is worth it. So you get more out of this extra, this specific way of doing computation than what you lose because you'll have to make your network smaller. So what that means is that ideas like experience model based on experience replay are not very good because they are very wasteful in terms of computation. Algorithms like an approximate model like maybe mu0 are somewhat better than that because they don't really learn an explicit model and use a lot a lot of extra computation for that. Now, when I was looking at papers that do model-based RL, like for a lot of them go completely against this idea that you need to computate, you need the computation fixed. So if you look at, for example, Simple, it's a paper that came out by Berkeley, has a lot of authors, very popular. It uses about 50 times more computation for the planning part and the model-based learning part, and it's really not a reasonable comparison at that point. And this third part, which is really something that I've been thinking about, but I haven't thought a lot about, is that, well, we also need to develop algorithms that don't lose the capability to explore with time. So this is for the control part. And right now, if you look at most of our algorithms, they rely on initialization for their exploration. So either they'll start with a very stochastic policy, or they will have a large epsilon greedy policy, and then they'll decay it. And then once you're done learning, at that point, your agent is not exploring a lot. But if our goal is to do continual tracking, as I said, which can be good for big words, then clearly we cannot do that. We need to develop algorithms that can increase exploration based on experience. Okay, so that was just a small part of what I think would be reasonable directions for reinforcement learning algorithms to make them work in big words. Now the final part is just how should we benchmark our algorithms for these big words? So benchmarks are a proxy to the real world that we care about. So ideally, we want to make benchmarks that are faster to run, but they still highlight the same problems that exist in our real world. So that means you can make benchmarks that are bad for your goal. So in this case, as I showed previously, that if your benchmark is such that it's very small compared to the agent, then it's possible that all the conclusions you will draw from those benchmarks will be misleading. And this is very similar to if you make assumptions when doing theory that are not true for your real problems, then a lot of the results you might get might be misleading. So we want to make a benchmark that tries to capture this property of big word. And we can do that by limiting the computation, communication, and memory that the agent is allowed to use. And this part is a bit subjective. There is really no clear way of figuring out what should be the size of my agent, the environment, so that we are satisfying this big word constraint such that the agent cannot just fit to the environment perfectly. But we can still use some subjective reasoning to come up with constraints that will satisfy it. And the important point is it's not that important to be very precise about it. The only thing that's important is that the environment is much, much, much larger than the agent, and everything else is not that important. And then once you have this constraint set up, and it could be in terms of computation memory or the amount of communication your hardware is supposed to do, then anyone is allowed to use any algorithm to solve that benchmark. And what you would hope to see is that a lot of these ideas that some of us care about, like online learning, continual learning, those would automatically emerge to be the superior solutions in these benchmarks. So I'm going to present one such benchmark that I've been using for my research. I call this the online Atari prediction benchmark. And this is the same benchmark that I used to show the results beforehand. So the goal is to do policy evaluation on Atari learning environment. And the policy is an expert rainbow DQN agent that was pre-trained by the folks in Chainer RL, and they released the weights we can use to generate policy. And then I'm going to make some changes. So like I said, we cannot sense the whole word, and Atari has this problem that you can basically sense the complete state. But we can fix that. We can just downscale our frames to be much smaller, 16 by 16 by 3, which gives it about 800 features, and they look like this. So if you look at one specific frame here, for example, this one, you can't really see the position of the ball. But if you look at the whole sequence, you can see the ball in some frame. For example, visible here. Similarly, if you look at other games, you see that for many, many frames, some things are not visible, and then sometimes they're visible. So by doing this, we get two benefits. One, now our experiments can be much faster without making the environment simpler. I didn't change the environment. I only changed what the agent senses, and that it satisfies the constraint of big word a bit better. And then this is just a rough number. This is something that I'm still tuning, but let's just say we're going to limit the resources of agent to 50,000 floating point operation per step. I'm not really adding memory and communication constraint because it's really not easy to do that in a concise way. So for a starting point, I think this is a reasonable thing to do. And then the evaluation can be just, we're going to look at the error that's averaged over many time steps. Now, a consequence of using this benchmark is small choices that we don't care about suddenly matter quite a lot. So imagine you're using feed-forward network with one hidden layer and using backstop. If you only use the current sample for learning, then these constraints will allow you to have about 33 features. And let's say you're using a buffer with a batch size of 1. Now you can only use 22 features. And this might be a bit odd because I mean you're learning with one sample in both cases, but the thing with buffer is that you need to first process the current frame for prediction, and then you need to sample a frame and then process that frame for learning. So you have to do some extra computation. So you can see that these two things that probably no one thinks are important. Should we use the current sample or should we just sample from the buffer of batch size of 1? Probably not important for most people. They suddenly become very important when you design a benchmark with these constraints in mind. If you use a batch size of 2, the agent becomes even smaller. 16, it only has 4 features. So if, at this point, if I ask you, okay, which one do you think is going to do the best? My money is on this first one because 33 features are not that much for a remote party, and then losing capacity is worse than the thing I would gain by using buffers or larger batch sizes. And the other nice thing about this benchmark is that because it's prediction, we can do some optimizations to make it really fast. So for example, these experiments, you can do 50 million steps in 1 hour on one CPU, which is around 100 times faster than if you're doing the normal Atari benchmark. And again, someone says that, okay, I've made the problem easier by doing this. That's not true. The environment is the same. The problem is the same. I made the problem harder, if anything, by making the observation much worse.
How many features are there in other words? 16 plus
80,
16 plus 3?
84 by 84. 84 by 84 by 3.
For any other problem, 16 times 16 times 3, 5800.
Yes.
And you can only use 33 of them.
For 50,000 operations, yes, because if you have a fully connected feed-forward network, then you have 33 features, and you have 800 times 33 rate maintenance time. So if you use a full connected network, you have to do a lot of computation for that.
33 is the number of features.
Oh,
Yeah, so that if you use a sparse network, then you can use more, right? So maybe suddenly sparsity becomes more useful. Maybe you don't want this dense, fully connected network that people use once you go here. And then this number is small enough that you can do sweeps over all the games and sweeps over parameters and then get statistically significant results with the computation that is available to us. So in my experiments that I haven't shared here, we ran experiments on some 40,000 experiments overseas and have parameters and got very nice and clear results using this benchmark. Okay.
okay, question.
Yes.
You say that 50K loss. I
Yes.
think that's like computational capacity. Is that the computational capacity of the algorithm, or it's the computational capacity of doing a feed forward, or it's like feed forward plus back forward?
It's the full algorithm. If you're using feed forward network, then it's feed forward, backward, and everything else.
And everything, let's say you maintain some queue, and then any operations on that queue also counts as.
Yes. So all you can use it however you want. You can use a buffer, or you can use it however you want, but you have to count everything. And these are the amount of resources you have access to. It's not clear to me how to enforce this in a good way. That's something that I'm thinking about. The one way could be if your hardware is fixed, then you can convert it into time and say this is the amount of time you need to output a prediction. But I don't know, maybe that's a better way.
Right, so that's something like we need to know, like you know how to efficiently implement an algorithm. Because sometimes you may keep some buffer, keep some memory, and then that can save the computation.
So then that would become part of your algorithm, right? So if you can do computation more efficiently, then you have a new algorithm, which is computationally more efficient and better.
That's implementation. No, implementation is about computation. Like if it's just an idea, then you don't need to say about this computation, but computation rather than the same computation.
I don't think I follow. Are you saying that you could have same algorithm and two implementations, you
Yeah.
could use a different amount of floating point operations?
You implement the replay buffer by a DQ versus like a table versus something
So,
else.
so I would say that how you implement it is part of the algorithm. Like a fully specified algorithm would tell you how you're implementing it. It won't, yes, we do it like this, that, okay, I'm throwing it in a list. I don't care if it's implemented by a hash table or a tree, but really, if you want a fully specified algorithm, you have to say those things.
Right, so I guess maybe he's saying that maybe it might make comparison had across paper, like someone might have used, an experience you play with DQ, but you're saying that they should specify all of these things so that, if you want to compare across with them, then maybe you can implement it with the same sort of constraints or something like that. Right?
Yes, so I do agree. It's very challenging to figure out how to implement this practically. The way I do it is because I'm doing all the experiments. I can just make this sure it's all there, but might not be. Maybe it's not a good benchmark comparing across papers. You should run all the experiments yourself. In this case,
Yeah.
So I didn't run for the feedforward case, but I ran for the recurrent networks case and this one that just uses the different sample and picks the biggest function approximator. That's the best.
Oh.
Because really more capacity is what you really need in this problem. Otherwise it doesn't do well. Okay, and it's similar to what that the comparison in the beginning, the RTRL versus backup, and like one is simpler and one better. So okay, so what are the conclusions? Conclusions are that algorithms that work well in over-parameterized setting can perform poorly in big words, especially if you compare them to more computationally efficient algorithms. And then even though computation is getting cheaper over time, we still need computationally efficient algorithms because the bottleneck is capacity and not and can always get benefits by making our agent larger. Not always, but if we can do it, we do it smartly. And then the need for continual learning emerges naturally in big works. There is no need to motivate it by using external factors, which is what's done in a lot of the research right now. It's a solution. You can think of continual learning as a solution method that outperforms fixed solutions when you go in these large works. And then finally, if we want to figure out which algorithms are good or not, we care about these big words, then we have to design our algorithms very carefully so they satisfy these constraints. So that's about it. Thank you for listening. And if you have any questions. Yes.
Yeah, thank you. Actually, wonderful talk. I wonder what's the intimate moment for you to possibly look like? Because I mean, the benchmarking setup is wonderful, but I think if you talk to people who have access to, let's say, adequate computing to hear,
Yes.
right? So it's almost like you have to have a setting where if you do not do, let's say, the right kind of computing learning, then you're going to boil the ocean. Right, and so or maybe climate change is going to get in your way, right? Or you're going to die before you talk to people. So what would that kind of setting be like?
So I think my model is that if you take some of the real problem that people are trying to solve and things are not working well, and what they're doing, so let's say they have, a lot of competition, 10 GPUs, and using 10 GPUs, they apply a very expensive algorithm on it. We can come up with a good algorithm in this setting, then we'll say, okay, use my algorithm, still use the 10 GPUs, but now your function approximator is going to be very large. It's going to have maybe 1 trillion parameters as opposed to 10 billion parameters. And then you can show that in these large settings as well, look, these very large models, which you are training with the same amount of resources, are outperforming your methods because the constraint really is the capacity in this case. So, for example, in this case, I limited the computation to 50K flop, and I'm using one CPU, but I did some computation a long time ago that what can I do on one GPU if my algorithm is very cheap? And you can train like 100 billion parameter model on one GPU. That's pretty large. And then if you can show that using one GPU, which is how much D2N uses, and trains a tiny model, I can use the same hardware to train a much bigger model and outperform those tiny models. That would be, I think, the big win.
Yeah, so maybe this constraint is like more general, right? Like, yes, this is a good benchmark for perception, for example, in this prediction case, but I guess everyone in the room can sort of use this constraint to whatever problem that you right, like whatever problem they're interested in, you can just say, okay, if we have a limited amount of computation, how do we use it well? And of course, we can add memory and communication down the line, but
Yeah, I think that's true. I try not to say limited because then people just assume I'm trying to, do embedded system. If you have a fixed amount of computation, how do you use it efficiently? And yes, you can do it with anything, with any problem. Like the model-based RL case, you can do it by, making sure that this comparison of model-based RL versus model-free RL. You can do the comparison fairly by keeping a computation fixed. People don't often do that. And 50 case loss is not even a good constraint because really what you really care about algorithms that can be parallelized versus algorithms that are sequential. It doesn't capture that and a lot of other important things. But this is just something that's easy to communicate. So if you make it too complicated, I think no one is going to pay attention and use it.
Yeah, I don't know if this is a bit abstract, but science is a big world problem. And as a society, we continually learn about how the nature works. And one thing that's known about scientific progress is it occurs in paradigm shifts. So some point that the paradigm completely changes how we think of the world, a new way of thinking, new representation thinking. Are current online continual learning frameworks capable of that quickly to actually change the representation? Or would you need something like a swarm of different cases which can be doing this at the same time?
I mean, the current algorithms are very bad. They won't do well at all. But to add to the point you said, like science is a pretty good example of how the progress that we're making is allowing us to collect even more fine-tuned data, high frequency, high resolution. And the problem is it just keeps getting harder, right? Like now we have brain data, which is significantly more high resolution than it was 50 years ago. But yeah, no, I don't think we have algorithms that can do very simple tracking well. And what you're asking is much more than that.
so whether algorithms can adapt to these changing things, maybe I feel it's more likely that we'll have to teach our algorithms to have that capability rather than expecting our current algorithms to be able to do that. So I think we are still awaiting a paradigm shift into that capability.
Yes.
So if we're facing like a new problem, can we decide whether our model choice is like over-parameterizing or not? Or we have to
Yeah.
use
So the way I think about it is that we should just maybe pick problems that are so large that there is no risk of being over-parameterized. This is not true for the Atari case, right? This is artificial, but really you can make a benchmark that is so large that you go buy the best GPU in the world and you're still going to be under-parameterized. The only downside of that is that nothing works. And then if nothing works, people just give up instead of saying, oh, if nothing works, maybe I need to develop new algorithms. Yeah.
I mean, but maybe we can make it work for simpler problems too, right? Just say that, oh, for any simpler problem, you will have like maybe some benchmark results in the community, and then maybe just say, oh, I'm going to use 1/10 the parameters. Things are probably not going to work. Now let me work with that. Right?
It's just that I think practically the community doesn't respond nicely to that because they just, no, scale is good. You're scaling things down. I don't like that. So I think the way to communicate with them is to say that, okay, I'm not going to make my agent smaller. You keep your agent, you're keeping a large agent, keep it, just make the problem harder. Don't solve the problem you're solving. I think that would be, because then I'm challenging them to say, no, make it harder, not making it easier for them. And then they can't say scale is all you need, you're wrong, and stuff like that.
I found the example, the AlphaGo 0 versus the 1x, for example, very intriguing. And also, like in PE especially, like you were talking about implementation. Because if you draw the boundary, like around the agent, you say what about. I just wonder whether the big world hypothesis also applies to the agent itself. In a sense, actually, if you, let's say, including condition specifics as part of what is inside the agent, then the agent also becomes big, right? And in order, so maybe we can call it instead of like big world hypothesis, we can call it the rich world hypothesis, right? And the internal world will also be very rich, right? I mean, that has been, let's say AlphaGo zero network versus one network. The intuition actually, the network is big enough, right? Such that you cannot easily suck out, right? Like what's in there, right? You have to drive in the right way. I assume what you were, sort of implying is actually you have to drive that with the real world aspect, right? You mean a big, go games, right? So you cannot just drive that kind of like, let's say for a vision or something like that. So whereas if we go with like E's suggestion, right? Look, what if I have quantum computing, right, as part of information, right? So like then how do we count operations? Because those are already abstractions over the real information, right, which is included inside the. So therefore, I wonder is what's really going on. Is this really like inside outside, therefore small in big world, or is this actually something different? Is rather sort of richness versus abstraction. Okay. It's very philosophical. Yeah, that's the question.
I don't know if I fully get the question.
I mean, for example, if you replace the internal computing with analog computing with quantum computing, right?
I see.
Suddenly, how you count?
Yes. So there is this thing, right? So that's why. So when I was making this, a very glaring problem with this is that I'm really forfeiting to the hardware we have. So then, what's the real constraint that should be? Like one could be energy. For that as problem, that just means if it will make your system more energy efficient, then you improve your results. So hardware research improves your benchmark suddenly. But maybe that's fine. Maybe you do eventually care about the energy used, right? And that takes into account all these memory communication. Like sure, you can like a bottleneck. Downside of using communication that's too much is that you use more energy, even if you're not doing operation. So maybe that's the right method. But even that's not perfect. I don't think there's a perfect way of doing it for scientific study. I think it's just subjective, but doing this is better than not doing this.
Is it fair to say like just the meta constraint should be make things fairer, right? Like in the sense, like one of the moments earlier, which was similar to this, was when people realized, hey, when we compare two algorithms on like the same episodic problem, each of the episodes could be very different lengths for both of the problems, right? So they could be using one algorithm could be trained for a lot many more time steps than the other. And then people realize, okay, maybe we should train for the same number of time steps that sort of equalizes this thing. So I guess this is something similar to that, where we're saying, okay, just be mindful of how you're doing the comparison, and then as long as you can make it fair, whatever it takes to do that,
I agree with it. It's not worth it trying to be too religious about it.
Change the topic a little bit. You said that you need a perception module that can keep track.
Yes.
But then what do you have to say about image map or success of deep learning in image classification? Like the current models seem very good at perceiving images. They can classify what's in the image very well. Then does the big world hypothesis really make sense?
I mean,
Is it really relevant in that case?
in that case, maybe not. If you have a fixed data set and you go to fit it and you can have a large enough model, probably don't need it.
No, but if you use it in real world, maybe it still works.
Well, it cannot recognize people. There are 7 billion of us. So imagine you want to fit it in that information in the model. Now suddenly maybe it doesn't have enough capacity. There's so many other things, right? If you want to identify individual, not just that it's a Honda. You want to identify it's a Honda that belongs to this person. And then it becomes again very complicated. So
I have a very limited understanding of neural networks. A lot of their success comes from because they're over-parameterized. We are nice things like over benign overfitting or implicit regularization. As soon as we give up that, do they still seem appealing, or like why did you, for instance, one example could be why did you use neural networks in your big world?
Right.
Questioning what should we look at them? Maybe
So-
neural networks are not good.
yeah, to answer the first question, I think it should be our existing solution methods only work with neural networks when they over-parameterize. So it might be a problem with our algorithms and not neural networks in general. That they only really work if you over-parameterize them. And I have a hypothesis for that, which is maybe not hard to communicate it very quickly, but if you have a larger network, then you might already have better features that by just chance. And then if you train it, you just tune those features. If you have a small network, you won't have as much of them. So you're doing a smaller random search, or so you're doing a bigger random search with a large network. But that's a very stupid hypothesis. Why did I pick neural networks? The nice thing is they're very distributed, so they are more scalable. You don't need a lot of communication to implement them. You can implement them in distributed machines like GPUs. But I do think that they have very nice properties to be careful. But I'm changing them a little bit to get rid of all these sequential operations they do. So for example, the feed forward operation is sequential. Just get rid of those. Backprop is sequential. Get rid of them. And make it completely distributed.
Okay. Thank you, everybody, for your great questions. Thank you, Khurram.
Thank you.